Hi, in this tutorial I will demonstrate how you can solve stack cookie 1 and 2. After fetching rig 4, you can have directories like this, and then let's get into stack cookie 1. And let's take a look at the stack cookie 1 source code first. And what it does is it has a main, non-main function, and then inside the non-main function it calls an input function. So that's our target function. And then in the input function, what it does is it has a buffer with the buffer size, but it will read up to buff size multiplied by 2, so it will definitely overflow the buffer buff. But some of the special things so it will put the stack cookie, this value, FACE-B00C, this value at the EBP-4 as a stack cookie, and then after running the read function, it will get the cookie as a retrieved cookie value from the EBP-4, and then if the values are mismatching, then it will print out stack smash detected and exit. So basically it will put the stack cookie value, fixed value, at the EBP-4 and then check that, and if you cannot pass this check, then it will exit. So you need to make a retrieved cookie value from the EBP-4 should be equal to this stack cookie value. Then this is a basic what this program is doing. Then to match the stack cookie, let's take a look at the binary program. So I will open this source code, and then at the same time I will open the debugger, stack cookie 1. Then I will disassemble input function, and then so the first part, getting the stack cookie value into the EBP-4, that's actually coded in here. So it will get the value at 0804A02C to EAX, and then move that EAX to EBP-4. So let's check the value at here. So that's the stack cookie. Yeah. And then it will run read function, and the buffer address is at EBP-88. So you can overflow 88 byte, 0x88 byte plus 4 for the saved EBP, then you can overwrite the return address. But before going there, because this EBP-4, that value is retrieved at here and then compared with this value. So this is the stack cookie value, and then the value at the EBP-4 need to be matching to the stack cookie value. If not, jump not equal if both values, so this stack cookie value and the EBP-4 EAX is coming from here. If they are not equal, then it will jump to input function plus 89, and then it will put stack smash detected, right? And then exit. So what we need to do is we need to put this stack cookie value to the exact location of the EBP-4 to pass this check and successfully overwrite the return address and then make the program return. Because if it calls exit, then it will not return and then just kill the program. So let's do that, and then we will write an exploit script. And then we need to import contools, and then we will run process Q1. Then our target cookie value is this one, and then our buffer is look like a buffer at EBP-88, and then at stack cookie is at EBP minus 4, right? Yeah. And then this is at EBP minus 0x88. Then this is at EBP minus 4. And then we will have save the EBP here. And then return address. So we can construct our buffer as 0x88. No, not 0x88. Maybe the 0x84 to not overwrite the stack cookie value, and then plus the 32 cookie value. By doing this, we can put this cookie value exactly at this location, and then we can put the save EBP as blah, and then we can put the return address. And then we will use shellcode to execute our program. And then let's get the shellcode first. I will just use non032, my version, so you can use your own shellcode for this one. Then copy this, and so here's my shellcode, and then I will put my shellcode in the environment variable area with lots of knobs. So it's something like I will create the shellcode variable, and then I will add 10,000 knobs and then shellcode. And the reason why I do this is like this environmental variable is a huge one, more than like 10,000 bytes. In that case, I can set the shellcode address as somewhere in the stack. We know that the stack starts with the df something, and then if I use a d300, because stack starts at the FFFE000, and then E000 minus the FFFD300. This is definitely less than 10,000, but the somewhat bigger value that to bypass all the environmental variables. So I will just use this value, and then you may use like the D100 is all okay. Yeah. Make sure that you put enough knobs to better estimate where your shellcode is. And then I will just set it like this, and then I will send the buffer, and then see the result. But at the first run, I will just use a cookie value as a different one, just 0. And then let's try to run it. So it says stack smash detected. But if we match the cookie value, oh, it is a segmentation fault. And then let's see what happens. So FFFFD100 does not contain the shellcode. Then let's see. Oh, I didn't put my shellcode, that's the error. Silly mistake. I need to put environmental variables, then it will get the shellcode. And then to test it, let's set the cookie value as a 0 first. Then you can see that the stack smash detected. But if you match the cookie value and then match all the buffer and all these things, then you can get the shell. This is the stack cookie 1, and let's move on to stack cookie 2. And take a look at the source code, and then basic structure is the same. So it will call main, non-main function, input function. But the different thing is like now stack cookie is set as 0 at the first, but it will run srand time 0. So it will get the current time and seed the random number generator, basic random number generator in C as the current time, and then get the random number to set it as a stack cookie. And let's check if that is actually some of the random value. So for example, we can attach GDB to stack cookie 2, then can break it the main function, and this value right after the rand call, it will store that as a stack cookie. So this value is a stack cookie, and then we will break at main plus 52. So right after the running the rand and then storing the stack cookie, and then run it. Then print the stack cookie value. So it is 19F4546A. Then I will run again. It has 777265CC. Run again. So you can see that the values are changing. So because it will get the value from the random number generator. So that's how it works. And then it will put that random number stack cookie at the EBP -4, and before returning it, your retrieved cookie value should be equal to the random number stack cookie value. So now the task is like you need to guess the random number and pass the stack cookie check to launch a buffer overflow attack. But you might think this is somewhat ridiculous, but this is totally not ridiculous at all, because using this kind of the random number generator is quite weak. The reason is srand is a deterministic function, and then seeded with the current time. And on the system, if you call this time 0, so the granularity of this time counter is the granularity is per second. So if you run the program with the srand unsigned in the time 0 at the same time of this program runs, then within the same second you will get the exact same seed and then exact same random number. And we will do that in the Python script. So in the Python script, we will run srand time 0 and then also run the rand function to get the random stack cookie, and then we will pass the challenge. And before doing that, let's check if we can do the simple test. For example, I will create a.c, and then what I will do is srand 0 and then print out that value, rand value. So A and B are the same program, and then I will run A and then B. So these two programs are returning the same value, and then if I run within a second, you will see that the random value are the same, because the seeding value, the time 0, the granularity of that value is 1 second. So within 1 second, we will have the same value like this. So what I will do is we need to guess the random number. So in the Python script, we will run exact same function using C types, and then call the srand and then time 0, and then rand function to get the stack cookie value, and then launch the same attack as stack cookie 1. And let's do that. So we will write the exploit script, and maybe we can copy from the stack cookie 1. So I will change this to stack cookie 2, but now we need to change the stack cookie value. And to change that, so I will import everything from C types, and then in C types there's some object called the cdll, and load the library. This command, you can load libc.so.6 library and as in the Python script. And then by doing this, you can call any kind of function in the libc. So for example, what we want to do is we want to call libc srand and then libc time at 0. So this is equivalent as srand time 0, and then we can run cookie value. We can get the cookie value by running libc.rand. So this is equivalent as running the rand function. So this C types and then the CDLL library, this is quite convenient. So you can write any kind of the code in a shared library code, and you can call the function in Python script. After doing this, we can remove this cookie value stuff, and then to match the time, because the time of that we execute this program and then time of the doing this should be not apart less than more than 1 second. So this two step need to be executed at less than 1 second. In that case, our exploit will succeed. So just getting the random value from here, and then at the end maybe we can print what was the random value, maybe x %x cookie value, and then we will run it. So we got the shell, and then it guessed the random value correctly. Then to see if it is changing, yes. So it guessed the random value correctly, and blah as the save the UP, and then it will write the return address to our shellcode.